defined as follows. You take row A, you look at all the local data in row A, say all the expectation value of local observables. You form a new state, which is the state of maximum entropy, consistent with that row A, locally. So for example, it has the energy expectation value correctly, but it doesn't necessarily have the long distance correlations correctly. It only has local data correctly. Then you could easily show that it's just usual thermodynamic kind of argument that this sigma is E to a local Hamiltonian. And because this state is maximum entropy state, which is consistent with rho, it has more entropy than rho, because rho is consistent with itself. So whatever sigma is, it has more entropy. But it's also local, so it has a very nice structure. So it's like we take this state with a possibly non-local entanglement Hamiltonian, we turn it into something with a definitely local entanglement Hamiltonian at the cost of introducing, possibly raising entropy a little bit. But then we argue, there's a detailed argument in the paper, which I invite you to look at, and we actually prove a theorem for the case of frustration-free Hamiltonians, and give an argument for general case, that this entropy of this state is bounded by the area with some prefactor times the log of the Ernst degeneracy of this Hamiltonian. So in other words, the entropy of the state sigma is some area law thing which is non-universal, plus possibly the number of degenerate ground states of the Hamiltonian of the system with a boundary. But that's something we can also access via the RG procedure. We can imagine doing the RG construction for that case, and what that implies is that this cannot grow faster than L to the D minus 1. So here the entropy would have to be as big as L, it'd have to be R to the D minus 1 log R, if R is the radius size. But here this says it can't be bigger than R D minus 1. So this seems to rule out S equal to 2, S equal to 2 D minus 1. So I think at least for frustration free, it's actually a theorem. You can look in a paper for the case, for the more general case, I think it's a very strong argument. But the background assumption here is that everything is an S source RG for some S. If that's not true, then this has no force. This doesn't rule out everything. So, as I said, everything I'm aware of is an S source RG fixed point if it's gapped. But maybe there's something else out there in the world, some mysterious thing. That would be great to know. But at least within this framework, it looks like everything has to obey the area. Okay, so now we're going to get into really different territory.
I'm sorry, just
in
the Haas code,
yeah.
The degeneracy basically does not really scale with the system size. It just jumps between.
Well, yeah. So if in Haas code, if L is 2 to the k, then G is equal to 4 to the L. I think. Okay. So it doesn't grow. I mean, Ha is D equals 3, S equals 2, and so actually that the cutoff is S equals 4 in 3 dimensions. So Ha's code automatically obeys the area law anyways. So what you have to imagine is there's something like Ha's code, which has S equal to 4 instead of S equal to 2, in order for you to find a violation of this. Now we know actually that's going to be hard to find because Ha's code is also commuting projectors, and that automatically obeys the area law anyways.
That's true.
So commuting projectors can't, if they are S source RG, they can't be S equal to 2D minus 1. So you're gonna find some kind of frustration free but not commuting projector or some more general Hamiltonian to find a counterexample. So it unfortunately it'll be hard to sort this out in the near term.
But your proof of the bound on the degeneracy is based on law.
Yeah, actually that's let me point this out. This statement right here, S less than log G, actually does not rely on the S source framework. That's an actually independent argument. So that does seem to suggest that if you did have such a area law violating gapless phase or gapped phase, it would have to have a very large number of ground states. And so actually, yeah, there's kind of independent statement that everything with a ground state degeneracy which flows slower than LD minus 1, E to the LD minus 1 obeys the area law. So that's another theorem which comes out of this argument.
Sorry, I missed if you mentioned that there is a bound on how quickly the ground-state degeneracy could grow from some very general considerations.
From some what considerations?
Did you mention something of that sort?
Sorry, I didn't hear the first part.
Sorry, did you mention there's any bound on how quickly degeneracy could grow for a reasonable physical system? Did you mention anything of that?
But not for S source. For some just for general gap system.
Oh, okay.
No, I don't. Yeah, I don't know of a bound for. Well, okay, there is some relationship between the entropy and the degeneracy.
Right.
And for S source, then there's a bound,
Okay.
or there's actually a formula
I see.
for how the degeneracy grows the system size.
I see.
Right, it's this formula.
Oh, it's the G to the power S.
Right,
Oh,
log
yes, I see.
G2L equals S log GL.
Oh, okay. Yes.
So yeah, so what this says is if S is equal to 2 to the theta, then transfer degeneracy goes like E to the L to the theta.
Oh, okay. I see.
But yeah, thanks for that question. That reminded me to point out that this bound indeed is, this particular bound is independent of the S source framework. So far I've told you about, okay, I've argued, or at least conjectured that the S source framework can encompass topological gap states. It includes Haas code. It includes square root states. It probably includes CFTs, includes Fermi surfaces. So it seems to include almost everything that I've ever thought about as a condensed matter physicist. I've also argued, so that's sort of an interesting condensed matter perspective. I've also argued that it gives you some powerful tools to tackle the problem of proving area laws for gap Hamiltonians, which is something of great interest in quantum information community. And now I'm going to talk about the application of some of these ideas to gravity, to quantum gravity. And this is going to be very, very brief, just a quick sketch reminder. Now, what's the connection between these S source RG picture that I've been talking about and gravity? Is there a connection? And the connection comes because of the entropy. So here I've drawn a picture where I have my lattice, let's say a one-dimensional lattice. And now I've kind of coarse-grained the picture. I've not drawn the unitaries explicitly. I'm just showing you that you're removing every other site at every RG step. So I go from 16 to 8 to 4 to 2 to 1. So it's a 2 to 1 RG scheme, just like how I've been doing the whole time. And I've just kind of drawn a schematic picture of that RG scheme. And now we can ask an interesting question. I proved this recursion bound for the entropy. The entropy of this RG fixed point has this nice recursive structure, but does that bound have any sort of more physical picture? And in fact it does. If you look at this hierarchical kind of hyperbolic graph, then what the recursion bound for the entropy says actually is that the entropy of this region at the top between the two red dots is actually bounded by some constant times the minimum number of bonds that have to be cut in this graph to isolate the red line from the rest of the world. So for example, you could cut this bond and all of these bonds and that bond. That would be an entropy bound which is proportional to the linear size of the system. That's a bad bound because there's a much better path. If you go down the network, you go down a logarithmic number of steps, logarithmic in system size in this red length. You go down a logarithmic number of steps, then the region has been shrunk to a single point. Now you can go across and then go back up. So you cut much fewer bonds this way. You cut only a logarithmic and system size number of bonds. And so actually, in this network, the entropy of any region is bounded by log of the region size. So it looks like actually that entanglement entropy obeys an area law in all cases. Although the entropy of this thing could be log system, could be log region size. In terms of this higher dimensional geometry, this emergent renormalization group geometry, the entropy of this region is actually still obeying an area law. It's just an area in a higher dimensional space. So we make this kind of switch in our mind. We say, forget about the original geometry. Let's look at this new renormalization group geometry. And in that new renormalization group geometry, the entropy always obeys an area law, at least a leading order. That's what this picture says. So that's a little simple, that's a simple little result for these sensor networks. It's just true that they can't encode more entropy than that. But the connection to gravity is that gravity has this wonderful property that areas encode entropies. The most famous example being black hole area being proportional to its entropy. But by now, only slightly less famous is the Ryutakinagi formula, which says that the entanglement entropy of some holographic conformal field theory, if you look at some region A, that's related to the size of a minimal surface in the dual gravitational geometry. If you look at the size of that surface in Planck units, that's this quantity here, that gives you the entanglement entropy of the CFT. So I'm not explaining holographic duality at all, I'm just telling you a fact which comes from holographic duality. So in other words, for example, n equals 4 super Yang mills and large N and strong coupling, where we believe such a duality is true, then there's a state of the CFT ground state. There's a dual geometry, which is anti de Sitter space. There's a bulk state. There's some bulk fields. Let's forget about that. So there's just a geometry. To compute the entropy in this state of various regions, you just need to look at the geometrical properties of this geometry. So for example, at this line, the minimal surface is a half circle, and you can calculate the area, the length of this circle, and its log. And you can easily show then that you recover the usual CFT entropy. And so the idea that I had several years ago was that this picture and this picture are very similar. That's the zeroth order idea. And in particular, if this picture were somehow rigorous, if we could actually show this picture described correctly the ground state, then it would follow this equation is true. Or at least if this is a bound, if not actually giving you the entropy.
So,
yeah.
In your previous picture, what is the, just how they made it, what's the bulk theory and holography theory? Can you say something?
Yeah, I didn't specify exactly, I read it at all, but let's just talk about the gravitational part. I'd say, there's some connectivity here, which I roughly equate to the geometry, to the metric. And I don't specify any of the other degrees of freedom at this stage. In fact, now I think we understand better a little bit better how to map. So there are also bulk degrees of freedom that you can map. But yeah, let's just say this is at this point it's a kind of crude statement, just a pictorial statement. Okay, but the point is that if we could prove that this graph does describe the ground state, and if we could show that this graph has some kind of continuum limit, then we would have established this result, this holographic statement. And so the fact that the S-source framework gives us a way to actually prove that, for example, CFTs, that maybe even any CFT, has such a graph, that this graph could describe with the right tensors, the right unitaries, any CFT. If we can prove that, then we've gone a long ways in trying to establish this kind of formula from first principles. Now there'll still be some extra ingredient. You'll have to put in large N, you'll have to put in strong coupling in some way, which we actually sort of know how to do. And I'd be happy to tell you about it offline later. And in fact, it's actually very interesting because it goes into the properties of the unitaries, and there's a lot of fascinating quantum information there and many other things. But let's just say that the idea is with this S-source framework, we can prove this is true, and then with some extra assumptions, we can establish a formula like this. And this formula is really nice because starting with this assumption that the entropy is proportional to the area, plus an extra term, which this says that there's also a correction due to the fact that there's bulk degrees of freedom here, and they can also be entangled across this surface. So you have to add that correction. That if you take this formula as given, plus the existence of the geometry, then you can show that perturbations of the gravitational field around this space have to obey Einstein's equations with the equivalence principle obeyed. So this matter must couple universally to gravity, and that gravitational field obeys Einstein's equations. So we showed this very recently in a paper with Mark van Ramstok, which just says, starting from this geometry and this formula for the entropy, and using only the properties of CFTs, a property that all CFTs have, we're able to show that perturbations to the metric have to obey Einstein's equations. Linearized by de Sitter space and sourced universally by matter. So it's couples universally to the stress tensor of matter.
Yeah, so what do you mean by that? I mean, how do you define the metric? You know, Einstein equation is equation for metric.
Yeah,
All the metric appears.
yeah, the metric just appears. I just start from here. So I say there's a geometry. So the metric is, you know, is.
You're using the error law to define metric.
Yeah. The metric is just, you know, G-ADS plus H, some small h. And then I just assume that this equation is true. That's
Error law.
yeah.
Error law.
That's area law. Yeah, this is area of this
But
A
that's
tilde.
correction, the second term.
Yeah, this is a correction, which is the entanglement of bulk degrees. Sorry?
Do you ignore the second?
No, the second term is important. It's responsible for the equivalence principle. The first term just gives you free gravitons propagating on ADS. The second term tells you that all matter couples universally to the gravitational field. So actually, this is kind of cool. It says like, if I could, there's, you know, it's just everybody has the same amount of, you know, everybody contributes to entanglement in the vacuum. You know, you and I are entangled because of our electron fields have some vacuum entanglement. Well, I just put that term in there, and that automatically implies that everything couples universally.
So let's ignore the perturbation.
Yeah.
That is, so if you only use error law, you basically can show that the space is under the sitter. That's like the rule.
You can establish the anti-de Sitter just from symmetry alone.
Okay. And
But yeah, I mean the area
and
also.
then you add this second term is like a feedback, something like back direction. All right.
Yeah, it sources the perturbation. That's right.
Yeah, and then when you add the second term, basically you say that around this under this space you can get a linearized Einstein equation around this under this space.
Yeah, precisely. Yeah, so the statement is that the ground state of the CFT is dual to the geometry being an anti-de Sitter space configuration with all of the fields in the bulk in their anti-de Sitter space ground state. So now I consider a perturbation where I change the geometry and I excite some bulk degrees of freedom. That describes the most general perturbation, which still has a geometrical interpretation. And then from that, using only this equation, I show that the gravitational perturbation has to obey Einstein's equation, coupled universally to matter.
So how about temperature? Usually the mirror have to reproduce the Planck space if later black hole in the higher temperature case is more difficult.
Oh yeah, so this is all just near the ground state.
So you turn on temperature, can you still, this framework can still work?
I think it will, but you mean does this result
You
that?
should see this metric maybe not geodesic complete to some.
Yeah, you have to do some more complicated, because yeah. So yeah, the network is different. It's a mixed state. It's much more complicated.
So naively we cannot start from here.
From where you mean by here?
From this simple setup.
No, I mean I think this is still a valid equation even in the black hole background.
In the black hole background, the boundary just cannot temperature, but
Yeah.
then you fluctuate the geometry. In some sense, this metric may be singular at some horizon area inside the box. Then I wonder how one can see this just generalize this kind of picture.
Yeah, I'm not sure. I haven't thought carefully about that case, so let me not speculate on it too much right now. That's a good question, but I don't know the answer. Maybe you have
So
something.
I was just wondering, if that argument takes you beyond linear perturbation, linearized Einstein equation.
It actually does, because the graviton contributes in this term here. The graviton is a quantum field propagating on this background. And so what appears is the stress tensor of the graviton on the right-hand side. The graviton stress tensor is quadratic in H. Now it appears as a quantum object, so there's a little bit of, not hand waving, but there's some gymnastics you have to go through. You have to be very careful about what contributes at certain order. But you can look in the paper, and you'll find is that it is indeed quadratic in H. And the coefficient is exactly what it would have to be for it to be the nonlinear Einstein equation.
So does it mean I recursively fit back and?
Yes. Yes. So I didn't talk about it, but we have an argument that it's more or less the usual argument, but that once you have the linearized equation plus this statement non-perturbatively, that implies it has to be an Einstein equation nonlinearly coupled to matter. And similarly, if you change this, in the way that you know very well, if you change this to wall entropy, which is at least correct for this killing horizon, then you recover the higher curvature gravity.
So just to make sure, so we don't say the perturbation obeys the Einstein equation. Do you mean linearized Einstein equation or not?
Well, I mean linearized coupled universally to a stress tensor of matter, but that matter includes the graviton, and the graviton is actually quadratic. So it's not actually a linear equation. It's like there's a sense in which both sides are the same size, so it's a systematic expansion. But if you view it just as powers of h, then it's actually nonlinear.
Well, so do you get a full Einstein equation or just the equation opposite?
This argument directly only gives this like quasi-linearized version. So then we have to give another argument, like saying with the linearized version plus say this formula, or plus some energy conservation, or there's standard arguments that take you from the linearized equation to the nonlinear equation. But that's a separate argument which depends less on entropy than this linearized argument. But yeah, I do emphasize the so-called linearized equation is not actually linearized in a certain sense, which is precise. That is, that there's a sort which is proportional to h squared, except that only the quantum mechanical, only like the graviton part contributes, not the classical shift in the expectation value. But we have a precise argument in that paper that there's no other operator that can appear even in the more general case. Okay. So we're almost finished up here. Let me wrap up. So yeah, so let me just say that, so the point of this excursion is just to say that the S-source framework is also interesting, at least to me, for purposes of quantum gravity, because it provides us a route to obtain something like this rigorously, which we can then maybe turn into this, which we can turn into Einstein's equations. So actually we could, from the bottom, from a completely well-defined lattice model, go all the way, at the end of the day, to Einstein's equations. So we have some kind of route to guessing, or to understanding much better what non-perturbative quantum gravity looks like. Yeah.
So supposedly, the gravity dual is also S equals to 1.
Yeah, I mean, quantum gravity is weird. I guess I don't know what S. Does quantum gravity have an S? Because it doesn't have a local Hilbert space.
Oh, in a way, we tried to do Fermi surface, but I don't know if we have succeeded in that course and whether we could play.
Yeah.
We could do higher than higher than 1 in gravity.
Yeah, that's interesting. I see. Yeah, another thing which is interesting to mention actually is that if you take this picture seriously, then you can study other geometries which have more entropy. So not NTU-CTP center space vacuum, but by turning on other fields, you can produce so-called hyperscaling violation geometries. And these geometries have enough entropy to encode an area law violation. But if we again go with this idea that geometry is related to entropy, then actually, or that the geometry is like a picture of a quantum circuit, then actually this is a geometrical picture of a quantum circuit that does exactly S equal to the d minus 1. So there's all kinds of connections where the S source gives you some perspective on holography. The holography then gives you a perspective back on the S source and gives you better confidence that it's sort of all one big framework that makes sense. Okay, so let me wrap up with a brief discussion of algorithms. So come back to the problem of condensed matter physics and say, or quantum matter, to put it more interestingly. Come back to the problem of only coupled quantum matter and ask, can we weaponize this framework? Can we turn it into a useful machine for solving arbitrary problems? So what have I shown, or conjectured at least, that there's a very, very large class of many-body systems which fit into this framework. And then it's easy to show that if I give you such a wave function, well, suppose I just tell you the unitaries, that there's a way to calculate local observables efficiently, meaning in time polynomial in some parameter. Okay. Now the bad news is that this polynomial is like a very large number, so it's like, you know, the bond dimension to the 18th power or something like that. So efficient really does deserve to be in quotes, because although it's polynomial, it's not really useful, at least for any sufficiently large bond dimension. So I think we really desperately need new ways of working with these objects, algorithms that are non-variational. Most of the work done now is variational. I emphasize a little bit in these talks the idea of producing non-variational algorithms to construct tensor networks, and showed you a few examples in specific classes of models. So I want to emphasize, I think we really, really desperately need lots of fresh thoughts on this subject. Because I hope I convinced you that this is a set of ideas which can actually describe and potentially give you a lot of power to calculate very, very interesting kinds of systems, very broadly, you know, beyond quantum Monte Carlo, beyond DMRG, beyond all this other stuff. But we really need to work on the practical aspects to make it into something that will really change the way we do solid-state physics. And so, yeah, I just want to emphasize, I personally think this is, you know, really wonderfully fruitful area, and it really warrants much greater attention. We were discussing at lunch the other day. I think there's maybe 4 or 5 groups in the world that work on these kind of RG sort of tensor network methods. So there's plenty of room for young people to get involved here. So the takeaway message is the following. I think every reasonable, and I don't define reasonable, but you know, fine. I can just make a list. You know, insulators, superconductors, spin liquids, Fermi surfaces, non-Fermi liquids, fraction quantum Hall states. Okay, we just make a long list. Everything I ever thought about, I don't know, maybe I'm not very well read, but every reasonable ground state, I believe, is an S-source fixed point. I've shown you over the last 2 days rigorous evidence for this belief in the case of gap systems and also for square root states. And I've given you some heuristics for CFTs and Fermi surfaces, and I think that the theorems will come not too soon, or not too distant for those cases as well. And I think if it's true, it's going to really change the way we think about ground states. So I encourage you to become an S-sorcerer. That, let me say.